Hello and welcome to our section on databases. Let's start with a simple question. What is a database? Really quickly here, a database is a collection of data and also a tool that we use to make it easier to access and work with that data. So why do we need databases in a course about Node? In real-life applications, our servers work with some data that they make available to the user in a client, something like our web browser. Maybe this data is a list of planets that we've done some analysis on, and we've determined that some planets are potentially habitable for humans to live on, and others are either not habitable, or maybe they're not even actually planets. In these real-life applications, we need to persist our data in our server so that it can be accessed if we ever update or restart that server. When we save data to a JavaScript array or a JavaScript map object in our Node process, it's not persisted. It's not saved in a way that will stick around. It's only temporarily available while that process for our server is running. If we ever shut down that process, we lose that information forever. The good news is that we have hundreds of amazing, proven pieces of software that we call databases that we use to help us persist our data. You might have heard of some of these: MongoDB, Redis, Postgres, or SQLite. We're really spoiled for choice when it comes to databases. Remember our create, read, update, and delete CRUD operations? We want to take advantage of specialized software that helps us to perform these CRUD operations in an efficient way. In a way where we can take advantage of the existing work that thousands of developers have already contributed to. When we take advantage of these specialized databases, the data no longer lives directly on our server process, in our server machine, but instead in a dedicated database server, a dedicated database process that keeps track of our data in the most efficient way possible. Our server then queries the database to update or access that data. And the database sends the appropriate records, the appropriate data, back in the response. Let's review some different types of databases so we can make the right choice on which database to use. I'll see you in the next video. Welcome back. There's two main categories of databases that we commonly use when working with servers. We have SQL databases, or SQL databases, and we have what are called NoSQL databases. We'll explore the difference between these two types by looking at two of the most common databases used. For SQL, we're going to look at Postgres, and for NoSQL, we're going to look at MongoDB. Now, these are two very common examples, but most of what we discuss applies to any SQL database, whether it's Postgres or MySQL, SQL Server, or Oracle. Whereas NoSQL databases tend to be more specialized and vary a lot more between each other. Without further ado, let's check out Postgres versus MongoDB. When it comes to the type of database that they are, MongoDB is what's called a document database. Our information is stored in JSON, these documents that look very, very much like JSON documents, with keys that are strings and values that can be things like numbers and strings or dates. Postgres, on the other hand, falls into what's called the relational model, which is what pretty much all SQL databases follow. Data is organized into tables which have rows and columns, and the tables are related to each other in some way. Relational databases really shine at modeling these relationships between tables of data. Whereas in MongoDB, our documents are organized into collections of these documents. Or in other NoSQL databases, things might be organized into collections of objects or key value pairs. It depends on the database. The overall idea, though, is that these documents include all of the related data for something like a planet or a collection of friends, all in one spot. Whereas with relational databases, data is generally split apart as much as possible. We might have a table that contains a list of friends along with where those friends live, organized by city. The cities would be organized in their own table, which has a relationship with the friends table, where a friend lives in a city. The NoSQL approach would be to include that city information directly in the friend's information, directly in the friend's document. Because that information is all in one place, NoSQL databases are designed to be queried more quickly. Alright, so we've been talking about NoSQL and SQL, but what do those actually refer to? Well, that's the query language that's being used by our database. At least, SQL is the query language that all SQL databases share. The query language is kind of like a programming language which you use to talk to that database, to get information from it. So if you know SQL, it's very easy for you to go from Postgres to MySQL or another database that shares that same query language. Whereas NoSQL databases basically don't use SQL. Their query language is not SQL, hence the NoSQL. They often have their own specialized ways of talking to the database and to query for certain types of data. Because of this, you can think of NoSQL databases as those that are specialized for certain tasks. The query languages in NoSQL databases are customized for specifically what that database was designed for, which in MongoDB's case was to make it really easy to work with documents while still enabling horizontal scalability. Remember our discussion on horizontal and vertical scaling? Vertical scaling, or scaling up, was when we added fancy new hardware to our servers to make them run faster without changing the code or the amount of servers. With horizontal scaling, or scaling out, rather than making our one server run faster, we instead add more and more servers, which can each share part of the work required to serve our clients or users. We divide our requests between each of these servers. Well, the same thing applies to databases. Rather than splitting requests with horizontally scaled databases, we add multiple database servers, each living on their own machine, and we divide the queries to those databases to share the workload, so that our server gets a response with the data that it's asking for more quickly. With MongoDB, it's primarily designed to be run in a way where it's horizontally scaled, with multiple database machines all sharing part of the workload. We have many instances of the MongoDB process running side by side. It's much easier to horizontally scale MongoDB than it is most SQL databases, where you generally take the vertical scaling approach rather than horizontal scaling. Now, the truth is, these days SQL is learning a lot from NoSQL by making it easier to scale SQL databases horizontally. And NoSQL is learning from SQL to improve querying capabilities and add additional safety around those queries, which are some of the advantages of the SQL language and the associated relational model. With SQL versus NoSQL, both approaches are constantly evolving, but they're still both specialized. They're both optimal in different conditions when you're solving different problems. So using what we've learned, let's decide what database we want to use right now. I'll see you soon. Before we move on and make our decision, there's one more commonly misunderstood aspect of databases that I'd like to discuss. I'd like to add to our model here the concept of schemas. A schema defines the structure of the data that we store in our database. For example, if we have a list of friends being tracked in our database, our schema would say that a friend always includes a first name, a last name, phone number, and maybe a location. This gives us the advantage of having our data be predictable and structured, which makes it easier to work with. With SQL databases like Postgres, our tables follow these rigid schemas that define, for example, what data is included in our friends table. SQL databases require that you know the schema of the data ahead of time when you initially create that database. In this way, SQL databases resist evolution. They're not easy to restructure. For example, if our database is currently being used by some application, we can't change the type of data that our tables hold very easily. Sometimes we even need to bring our database down to migrate our data from one schema format to another. This SQL approach is not great if we want our application to always be available to our users 24 hours a day, 7 days a week. Migrating schemas is a complicated topic that you could write books about. While NoSQL databases, like MongoDB, are more flexible. In fact, they're sometimes called schema-less databases, which kind of refers to the fact that they don't have schemas. But that's not entirely accurate. While MongoDB, for example, doesn't force you to have a schema, it's very easy to add schemas in your code at runtime. For example, we could have our API enforce the schema every time we read or write to our database. This allows us to take advantage of the performance and flexibility of NoSQL while also adding some of the safety and structure of schemas. We'll learn more about this kind of validation very shortly. For now, what we need to know is that with these different approaches, we need to trade off flexibility with predictability and safety for performance. It really depends on what we're doing. So without further ado, let's jump in and decide which database to use in our application. I'll see you in the next one. Welcome back. Let's add a database to our NASA Mission Control dashboard. It's always a good idea to start by thinking about our goals. We have two main reasons for adding a database to our NASA project. First off, we want to persist our data so that it sticks around when we restart our server, so we don't keep losing launches that we've already scheduled when we make changes to our code, or when we decide that we need to restart our server for any other reason. The other big reason that we want to persist our data in a database is because we've learned that when we run many instances of our server in a cluster, our node code needs to be stateless. When we handle a request coming in, it should only rely on the data that's being sent in the request. Anything else needs to come from a database or some other external service. Going back to our NASA project code, what this means for us practically is that inside our server, if we look at our controller files, those are under source/routes, and then we have a controller for each of our routes. The only state that our server should rely on is the data in this request object being passed in to our server, in our case, through Express. Any other data needs to come from external sources and services which are independent from our node process, from our node HTTP server that's running when we start it up from our package here. Okay, so that's how we make our server stateless. But what data are we actually storing? We can see in our models that our database will need to support a list of launches where each launch contains a few different properties, including a number, some strings, dates, as well as an array and some Boolean flags. And we have a list of planets that have been marked as potentially habitable. And the only real data that we're using from our list of planets is the planet name, which we use to list out the potential planets that we might want to target when we create our launch. So our launch, this target parameter here, refers to one of the planets in our model. So there is this relationship that we have where a launch target is a string that is stored in our planets model. But otherwise, all of our data is standalone. There's no complex relationships between the launches and planets. Now, the third and final piece of state that we store is this flight number, so that we know what the latest flight number is, and we can increase this by 1 for every new launch that's coming into our API. So our database will need to be clever about tracking these flight numbers, as we create launches in our database. It's also worth thinking about how our data will be accessed. Our launches are stored currently in a map, and each launch is looked up by the flight number. Each flight number needs to be unique for an individual launch within that entire list of launches. Whereas our planets are accessed in sequence to basically just list the values that are stored for each planet name. And our launch's latest flight number is used when we create new launches to assign the flight number to latest flight number +1. That's how our data will be accessed. Now that we have an overview of which data we're tracking and what our requirements are for a database, let's compare SQL with MongoDB and decide on which one is better for our NASA project. I'll see you in the next one. Welcome back. SQL versus MongoDB. Here we go. Oh boy, this is a hot topic and everyone has their opinions on which one they prefer. Let's try to take a step back from our preferences and see which one has the most advantages for our NASA project. Both SQL databases and MongoDB will meet our requirements to persist our data somewhere that lives outside of our node process. So how do we decide between the two? If we look at historical information, SQL was created back in the 70s and was really popular in the early days of the internet in the 1990s and early 2000s. It already had a few decades to prove that it worked, and it allowed us to store our users' information reliably. However, in the late 2000s and 2010s, NoSQL and MongoDB came along as we started getting these large websites. Sites like Google and Netflix with massive amounts of data that needed to still run very quickly. And more recently, SQL has been undergoing a resurgence, with database administrators and architects realizing that a lot of the things that SQL provides for us are still invaluable in the era of the internet and big data. We can't be so quick to throw those ideas away. In fact, some of the ideas from SQL, like more reliable transactions, have started making it into MongoDB and other NoSQL databases. The truth is, the best way to choose your technology isn't only to look at what's trendy. You want to instead pick the right tool for the job at hand, for the data that you need to store, the users who will be using your application, and the application flows that those users will be following when they use that application. In our NASA API, we can take a look at the routes that we support to explore how our data is going to be used. We can get, create, and delete launches. And for our planets, we can get the list of all of the ones that we're storing. The key here is that all of our responses, if we look at our controllers, always return JSON. And our server is written in JavaScript. In MongoDB, our collections and documents are stored as JSON as well. Or to be more specific, this BSON format, which is a close cousin of JSON. BSON stands for binary JSON, and it was built so that our Mongo JSON objects could be parsed more quickly. But it looks just like JSON. And that's the exact format that MongoDB stores our data internally. So we don't have to transform our data from JavaScript objects in our code to some other format like tables that are used by SQL databases. Things are much easier to reason about when we don't have this mismatch between how things are stored and how they're actually used. This is already a big win for MongoDB. And it's the reason why so many JavaScript projects tend to use Mongo as a database. In fact, MongoDB includes a shell when you install it on your machine, which allows you to make queries against the Mongo database. The way you query your data in this Mongo shell is by writing scripts in JavaScript. Even if you weren't already running Node, MongoDB already uses JavaScript as its internal scripting language. Now, if we compare this to SQL, there are some databases, my favorite being Postgres, which include JSON types. That is, they allow you to store JSON inside of your SQL tables. This makes it much easier to store JSON data directly in your database. However, that's not really what SQL is designed to do. SQL databases like Postgres work best with relational data, which is split up and decomposed into these tables that all relate to each other in some way. The way we organize data into tables doesn't often align with how we store it in JavaScript or in collections of documents in MongoDB. So we need to add an extra layer to transform our data into a format that works well with SQL. The fancy term for this extra work is the object relational impedance mismatch. All this means is that we have to map the way data is stored in a relational database like SQL to the way that objects are stored in our code. And those two ways of representing data aren't always very easy to convert from one to the other. NoSQL databases, on the other hand, sometimes allow us to completely avoid this issue by storing our data in a way that matches the way it's used in our code. For example, by storing JSON in our MongoDB database, which matches very closely with the way we store data in our Node JavaScript code. All right, so is that it? Does MongoDB always win out when we're working in JavaScript on APIs that always return JSON data? We haven't quite discussed the whole story. There are still very good reasons to use SQL in JavaScript projects. Let's continue our discussion by looking more closely at the data in our NASA project. Welcome back. To finally decide on a database, we're going to need to take a closer look at the data we're going to be storing. Mongo will be best for unstructured data, where we're storing large amounts of data And keeping the data structured is less important. For example, where the structure of our data is likely to change quite often. Mongo works great when the decisions that we make and extrapolate from our data are more important than making sure that data is structured perfectly. SQL, on the other hand, is great for when the structure of our data is known, and we want to enforce that structure. For example, banking and credit card information is already well defined, and it's more important that we enforce the existing rules of those banking systems. The way credit card numbers are stored isn't likely to change very often. What about our mission control data? If we take a look at our server models, starting at our launches, the types of data that we store are fairly basic and can be stored in either SQL or non-SQL databases like MongoDB equally effectively. The main difference is the relationships between the different types of data. So our launch, remember, relates to a planet in our list of habitable planets. This is something that SQL can model very well. In SQL, you would have the launch target referencing a planet in the planet's model. And the relationship would be that a launch has a target planet. But really, if we look at the planet's model, it's very, very simple. We're just storing the planets as strings, which represent the name of the planet. We're not storing very much related information around each planet. So we could store this planet's data in pretty much any database equally effectively. And we don't gain much by referencing the planet and removing that duplication of data between the planet's model and the launch that targets a planet. If our planet was instead a complicated object which referenced other objects, for example, we were storing a name, but also a list of moons that that planet has, which would be a list, each potentially referencing another moon. So moon A and moon B, where each moon would potentially be a separate object in a separate collection. In a situation like that, SQL would really begin to shine. And while Mongo does have some tools to add relationships between our data, if we eventually decide that those relationships are needed, it'll never be as good as SQL when working with this kind of relational data, with connections between moon objects and target planets and launches. So when it comes to the relationships between our data, SQL doesn't really give us much. Our actual situation here is that our planets are just as easily stored as strings as they are references to planets in our planet's model. So what other advantages does SQL have? Well, one of the best things about SQL is its reliability when performing transactions with that database. Transactions like create, read, update, and delete operations, or potentially more complex combinations of updates on different types of objects, for example, different tables in our SQL database. The guarantees that SQL gives us are really, really great. They're called ACID transactions, which guarantee things that we might take for granted, but are definitely not a given when it comes to complex data on the internet. or in complex systems and servers. For example, ACID transactions, which stand for atomicity, consistency, isolation, and durability, ensure that when you write your data, it's actually persisted and will survive permanently. That's the durability aspect. ACID also guarantees that, for example, your data will always be written as a whole. You won't get partial transactions where only part of the data that you've written gets saved to the database and part gets lost. That's the atomicity aspect of SQL databases. In MongoDB, on the other hand, your writes to the database are in general atomic and durable, but there are cases where they may not be. And if you wanted to combine a series of writes and reads or updates, the combination of those operations has no guarantee to be atomic. Only part of those operations may succeed. Whereas SQL allows you to group these operations together in what is called a transaction. These transactions are very powerful when trying to perform sequences of operations, and you need that guarantee that your data will all be written at once or not at all. ACID is a fairly large topic all on its own. But the important bit for us is that most of our transactions, most of our operations in our database are individual. We don't often do combinations of reads and writes for a single request. So if we go to our launches controller, for example, we can see the getAllLaunches just has one read operation to read all the launches all at once. The addNewLaunch does some validation and then just performs one addNewLaunch function, which in our model, we can see just does a single write to however we're storing our launches, to that launches collection. And finally, the abort launch does have two operations. We first check whether the launch exists, and then only abort if it doesn't exist. So technically, it is possible that we get that a launch does exist from our database, and then if we don't have ACID transactions, it's possible that this value changes, and by the time we abort, that launch no longer exists. So this is the one operation where we actually have multiple steps. But in the grand scheme of things, our abort launch function isn't very destructive if a launch doesn't exist. There's really no problem with, remember in our launches model, that when we abort, we just set upcoming and success to false. So with a database like Mongo, where we don't have transactions, we might need to check if this aborted object exists here, but that's about it. There's no harm in trying to abort a launch that doesn't exist. This is just extra validation so that the user knows what's happening with their request. The conclusion from this is that transactions, as we get them from SQL, aren't that important to us for our launches use case here. As long as our data is persisted, the guarantees that Mongo gives us are good enough. And in return, we get reads and writes to our database that are very quick to execute. And we get a database that's easier to scale horizontally by adding more instances of MongoDB. There's one more make or break feature that SQL can provide for us. That feature is the extra guarantees and constraints that Postgres schemas can give us. Let's take a look at one example. If we take one more look at our launches model, SQL could guarantee for us, for example, that one of the targets that we specify in a launch is actually one of the Kepler exoplanets that we've marked as habitable in our planets model by referencing those planets just like we talked about earlier. So in that case, a launch with a target that is not in the planet's collection would be rejected by our database. That's one of the features in SQL when you use a reference, or what SQL calls a foreign key. It validates that you're actually referencing an object that exists in that table, in that collection. This would be nice to have, but it also makes things more difficult when our planet's data changes. Maybe we've explored space even more and analyzed our data and changed which planets are now considered habitable based on the latest research. Our NASA data is likely to change, and the requirements around exactly what we need to consider and store for each piece of data isn't fully clear to us right at the start. For example, maybe a new part of our NASA dashboard will need to inspect each of our target planets and get data about the moons of those planets. SQL would be great at modeling those relationships if we knew about this ahead of time, but it's just a theory. If we want to be able to remain flexible, our Mongo schemaless approach will make our life easier when it comes to changing the model of our data in the future. So really, there's advantages and disadvantages to both approaches. We're still early enough in our development that we gain a lot from the flexibility of Mongo. All right, that was a really good discussion. We've talked about many of the deciding factors that would decide which database we chose in a large-scale, real-life project. We've talked about a lot of advanced concepts in theory. That's just how things go when you're in the planning stages of a project. But it's time. While both Mongo and Postgres would work amazingly well for our NASA project, it's safe to say from our discussion that MongoDB is a great choice for our data right now. We gain more from it and its JSON-first approach than we do from the extra guarantees that SQL gives us. Don't worry, we'll keep discussing the advantages and disadvantages of Mongo and SQL as we continue building our NASA API. Let's keep it going and apply what we've been discussing in the last few videos. I'll see you soon. Welcome back. We're going to be working with MongoDB, so let's get our Mongo database set up. We can start by going to mongodb.com, where we have a few options. We can install MongoDB on our machine locally by going under Software and selecting the Community Server, as opposed to the Enterprise Server, which gives us some extra features when it comes to security and how we store our data, but costs money. So if you'd like, you can install the Community Server on your machine for free. If we select that option, there's downloads for your operating system, whether you're on Linux, macOS, or Windows. running Mongo locally will work great for the development parts of this section. However, when working with databases, most of the time we work with databases hosted on the cloud, where the cloud is basically a term for a server hosted somewhere on the internet. The good news is, there's this really great service that hosts MongoDB databases that's free called MongoDB Atlas. Atlas gives you this cloud environment that's closer to what you would see in a large node application. If we go under the Cloud option and select Atlas, we're taken to this page, which allows us to set up a MongoDB database in a cloud that's managed by MongoDB's Atlas service. Let's take a look. We can start our sign-up process and sign up with no payment information required, either using a Google account or filling in this form. And once we're registered, we're taken to a page that looks something like this. There's quite a few options here, so I encourage you to look around. We can optionally, in the top right here, set up an organization for ourselves, or optionally name our project. However, the most important feature that we have is the ability to create a MongoDB database by clicking this Build a Cluster option over here. So let's do that. We're taken to this page where we can select the type of cluster that we want to create, each with a matching cost. So let's make sure to select the free tier here, which creates this shared cluster with some really good features, including encryption end-to-end. All right, let's go. Let's create that cluster. Notice that we're making a cluster of Mongo instances, which each share part of the load for our Mongo queries. While Mongo does make it much easier to horizontally scale your database compared to most SQL databases, it's still a fair bit of work to manage if you want to do this locally on your machine. With Atlas, it becomes a matter of just a few clicks. Atlas has really changed the game for MongoDB in how easy it makes it to scale your databases. It's really one of the big selling points for MongoDB, which is probably why they gave it this great free tier, to encourage developers like you and I to use it. So back to our interface here. We're presented with the option to select our cloud provider and a region. This is the cloud provider that will be hosting our Mongo databases. We can select AWS, Google Cloud, or Azure. Each will provide a different set of regions that you can select. I suggest you select one of the recommended regions, and I'll go for this default US East 1 region. Scrolling down, we can select the cluster tier, and we just want to make sure that we're selecting the option that's free forever, which gives us 512 megabytes of storage and a shared CPU that might be running some other applications. We also have up to 100 databases and 500 connections, which is more than enough because most of our connections are just going to be from our NASA API. We'll only ever really be using maybe up to 5 of these connections at a time. This number here refers to concurrent connections. All right, so moving on, we have some additional settings which we can only set up if we're on a paid tier, and we're okay with the defaults for now anyway. Finally, we can set up our cluster name, say calling it something like NASA cluster. And we're ready. Let's create that cluster. Okay, maybe we're not completely ready. We may have to do this catchpa. Let's see if that works. All right, our cluster is being created. This might take a few minutes to complete, but once it's done, we can connect to this Mongo database from our node projects. While we're waiting for this to complete, we can look around and see that our cluster includes 3 nodes that are each replicating our data. And we can go to this security option here, for example, under database access, to configure the security settings for our Mongo cluster. We'll start by creating a user which can access our new database. So if we go to add new database user, we can start by selecting the authentication method for that user. So let's select password and then create the username, which we'll call, say, NASA-API, as it's the API that's going to be talking to our database primarily. And we can type in a password here, or it's always a good idea for the best security to auto-generate a random password that's less predictable than anything that you or I could come up with. So I'll do that. If I click on Show here, you can see this secure password was generated. Now, this part is very important. Make sure that you copy this password and save it so you don't lose it. We'll be using it when connecting to our Mongo database very shortly in one of the upcoming videos. And finally, we can give the user that we're creating certain permissions. We want to restrict what our node projects will be able to do to our database. There's no need for them to have full administrative privileges on our Atlas account, say to create new users. No, instead, our user only needs to read and write to our databases. We want to follow the principle of least privilege. If we go to the American Cybersecurity and Infrastructure Security Agency website here, with this very serious sounding name, and we scroll down, we can see that the principle of least privilege states that a subject should be given only those privileges needed for it to complete its task. Nothing more and nothing less. So our database user generally only needs to read and write to our database. Those are the least privileged roles that we want to assign to our user. And we're ready. Let's add that user. And finally, now that we have that user to log into our database, we can go under Network Access to specify which IP addresses can access our Mongo cluster. Every machine connected to the internet has one of these IP addresses. And this list here specifies which machines, which IP addresses are allowed to connect to our Mongo database. So if I click Add IP Address, when we start using our database in production, we can select specifically the IP addresses for the server that's hosting our node project. That's the only server, the only IP address that's going to need to access our database. Because all access will be going through our API. And if our server is going to be hosted locally, we can select this Add Current IP Address option. However, for now we're in development. We may need to access our database from a few different IPs. So for now, I'll select Allow Access from Anywhere, which corresponds to this 0.0 access list entry here. And I'll confirm that, which means that with our user that we just created, we can access our database as soon as these changes finish deploying. To connect to our Mongo cluster, we go under Clusters and select this Connect option underneath the cluster we just created, which gives us a few options here. If we want to connect with the Mongo shell, with an application, or with Mongo's Compass application, we're going to be talking to Mongo with our Node application, so we'll select Connect Your Application. We're using node.js, and our version is over 3.6, which means we're ready. We'll be using this connection string here, along with the user and password that we created earlier, to connect to our fresh Mongo cluster. Let's find out how in the next video. I'll see you then. Welcome back. How will we connect to our Mongo database? We're going to use a well-known Node package called Mongoose. Mongoose is about the most widely used Node package for using MongoDB. More than providing just a way of connecting to Mongo, Mongoose has advanced querying features as well as features to create models from our data that follow schemas. Before we explore these powerful capabilities in detail, let's first connect to our fresh Mongo cluster. We'd like to persist the data in our NASA API server. We'll start in the source folder in our server.js. Right here below where we set the port, we'll create a constant for our Mongo URL. And we'll set this to the value that we got as our connection string. Whether this is locally on your machine with localhost or somewhere on the cloud like I have here. So that will be our Mongo URL. And remember, we need to make sure to replace this password field here with the password that we saved when we created our Mongo database. So paste your password here, and our connection string is complete. What else does it contain? We can see that it's using the MongoDB protocol to talk to using our NASA API user and the password that we just put, the cluster at this address over here. And finally, we have the name of our database and possibly some options that specify how we expect Mongo to handle our queries. Let's replace the database name with the name of the database that we want to talk to. For example, we can call our database NASA, and it will automatically be created when we save our first data using Mongoose. All right, so how do we connect to this Mongo URL? Well, Mongoose is a npm package, so in our terminal, we'll npm install Mongoose. And we can now use Mongoose to connect to our Mongo database when we start the server. So I'm going to require Mongoose. Up here, just below HTTP, I'll say Mongoose equals require Mongoose. And just below where we define our start server function, I'll use this mongoose.connect function, passing in the Mongo URL that we just set. We want to connect to Mongo before our server starts listening so that all of our data is available when we start handling requests from the user. And our Mongo connect function returns a promise, so we can await that promise, and optionally pass in some parameters into the connect function. Pretty much every time that you connect using Mongoose, you'll pass in 4 parameters into the connect function. If we don't specify these options, we'll get some deprecation warnings in our console, warning us that the best way of doing things is by passing in use new URL parser and setting that to true. This determines how Mongoose parses that connection string that we just copied into our Mongo URL. We'll set use, find, and modify, and set that to false, which disables the outdated way of updating Mongo data using this find and modify function. We'll also set use create index and set that to true, which will use this create index function rather than the older ensure index function. And finally, use unified topology, setting that to true as well. This way, Mongoose will use the updated way of talking to clusters of Mongo databases, using this unified topology approach. All of these are options in the MongoDB driver that Mongoose uses to connect to our database. The MongoDB driver is the official API that Node uses to talk to Mongo databases by the company that created the Mongo database. Basically, if we want to use the latest, greatest features in Mongoose and the underlying Mongo driver, we want to make sure that these parameters are set. Looks good. All right, how do we check that our connection is working? Our Mongoose object exposes this connection property, which we can access with mongoose.connection. And this Mongoose connection is an event emitter that emits events when the connection is ready and things have succeeded, or when there's errors. So we can do mongoose.connection.on open and pass in a callback to execute when things are looking good. So we'll just say console.log MongoDB connection ready. But since we know that the open event will only ever be triggered once, the first time the connection is ready, we can use this once feature that all Node event emitters have, which allows this event to only trigger our callback once, the first time it's executed. So we're just being explicit that the open event will only get triggered once. All right, so what about errors? Well, for errors, we can do mongoose.connection. And this time we'll use the on function. We never know when an error will get triggered. It could definitely be more than once. Our errors correspond to the error event in Mongoose that gives us this error argument with information about the error. So we'll just log it, and we could use console.log, but let's use the console.error function so that our console knows that this isn't just a regular log, but instead an error, and we'll just print the error object. Note that we can put these event handlers just about anywhere in our file, above our start server function or below, as long as we've already required our Mongoose module. I think we're ready. Let's see if we can connect to our Mongo database. Let's start our server up with npm run server and see what happens. Our Mongo connection is ready, and our server is listening on port 8000. We're now ready to put our Mongoose package to good use. Welcome back. We're using the Mongoose package to connect to our Mongo database. Before we jump into more code, let's learn what Mongoose provides for us and how it works. This will help us understand our database code as we're writing it. More than just giving us a way to connect to our data, Mongoose gives us some advanced features that make our lives as developers much easier. Mongoose gives us what it calls object modeling capabilities. Let's find out exactly what this means. To start, with our Mongo database, our data is all gathered together in what we call collections. Our Mongo databases are made up of one or more collections. Now, the actual data that collections store lives in documents. The relationship between them is that collections have many documents. A collection is made up of 0 or more documents. 0 if the collection is empty. And each document stores data in this JSON-like format that Mongo calls bson. That's about it. What we have here in green is what MongoDB is all about. Storing collections of JSON-like data that we call documents. Now, we mentioned that Mongo doesn't enforce schemas. You can look at Mongo as a schemaless database. It's up to whatever is accessing our Mongo data to enforce some structure on the data that lives in our collections. And that's one of the things that Mongoose provides for us. Mongoose, here in blue, gives us these schema objects, which are tied to a collection in MongoDB. Each schema maps to the group of documents inside of a collection. The schema lets us give the documents in our collections a structure that must be followed when accessing our data with Mongoose. We can say, for example, that a document's flight number is a number, while the mission name is a string. And we can say that our flight number and mission name are both required fields. We can't have a document without both those properties. This required property is an example of how Mongoose lets us add validation logic to our documents. And if we so choose, Mongoose lets us provide more advanced validators that can check that, for example, a phone number isn't just a string, but a string that follows a certain format, with dashes and with a certain amount of digits that are grouped together. The way we use our schemas is by creating models that use the schema. The model takes that schema, and while following the structure of that schema, allows some corresponding collection to be queried. The model is a bit like taking the schema, which lives in Mongoose, and applying it to a collection in MongoDB. To create a model, you take a schema and assign it to one of your collections. We'll see this in action very soon. But that's Mongoose in a nutshell. We can now take our models and in our Node.js servers, in our Node applications, we can query our models to get the data and documents stored in our Mongo collections. These queries can include any of our create, read, update, and delete CRUD operations. And our models give us JavaScript objects we can work with directly in Node. That's what Mongoose means by object modeling. Mongoose takes the data as it's represented in MongoDB and allows us to access it as objects in JavaScript. All right, we'll refer back to this flow as we build out our database code. But for now, on we go. Here we go. Let's take the first step in storing the data from our NASA project API in a NoSQL database. As we've decided, we're going to be using MongoDB and Mongoose. We're lucky. The routes from our REST API include the launches and planets collections. These correspond very closely with the collections that we'll need in MongoDB. We're going to be working with our database inside of our models.js files, here under our models folder. We'll be replacing the in-memory storage of our planets and launches with the persistent storage of a Mongo database, the same one that we just connected to. Let's start with a data modeling exercise. When data modeling, we're going to figure out the shape of our data and what schema it should follow. When working with a database, it's a good idea to start with our schemas and work from there. Once you know the shape of the data, you can use it as a reference to make sure that you're always on the right track when querying the data and building out larger pieces of functionality. Remember that our Mongoose schemas are associated with some collection of data in MongoDB. And these schemas determine the shape and structure of the documents inside that collection. What does this mean for us? Notice that so far, we've been using the sample hard-coded object here of a launch as a way of understanding how our launches data will look. We know that we have flight numbers, mission names that are strings, and launch dates that are date objects. Our schemas take this understanding that we have of our launch data and turn it into code that Mongoose can then use to enforce a certain structure, a certain understanding onto that data. All right, I know I'm sounding like a broken record here, so let's put this into action. We can make a schema by creating a schema file next to our model. You'll see the naming of this file vary from project to project, but I'm going to call it launches.mongo.js to make it clear that the code in this file will be specific to how we talk to our Mongo database. To access our Mongoose schema functionality, we of course need to import Mongoose. So we'll say const mongoose equals require mongoose, just like before. And this time, we'll create a constant that will store the schema defining the shape of our launches. So let's call that launches schema, and we'll assign it to this mongoose.schema object, which we instantiate. We'll create a new mongoose schema and pass in the definition of that schema as an object. So what does this schema look like? Let's piece it together. So we pass in this object, which will have a property for each of the possible data items that we want to store in a launch. So let's start with flight number. We'll create a flight number property in our schema, which we assign a type. For example, we can say a flight number is a number, just like that. And if we use this schema to try to save an object where the flight number is a string or some other type, that data won't be saved to our database. We can find the full list of possible schema types in our Mongoose.js website under the documentation. This is a great reference and includes a guide here on the left on schema types. If we scroll down, we can find the entire list of possible types that we can create. So we have our strings, numbers, and dates. We have Boolean objects and these object IDs. So now, for example, for our launch date, we know that's a JavaScript date object, so we can assign it the type date. But Mongoose allows us to do a little bit more than just assigning types to different properties. For example, we know that flight numbers are always required when creating a launch. We can capture this in our schema by assigning flight number not just a type, but an object, where we assign the type explicitly by writing type and assigning it to number. But then we can also say that the flight number is required and set that to true. And we can set other properties here. We can set a default flight number, say 100, or we can even set a minimum flight number and a maximum. Maybe we can't have more than 999 flights. There's a lot of room for validation that Mongoose lets us support. But I find in general it's good to keep our schemas simple when we're starting out, and our NASA dashboard doesn't really have a minimum or maximum flight number, while the default is just the flight number of the first launch that we create, whatever that is. So for now, what I'll ask Mongoose to verify is that a flight number is indeed a number and that it's required. Those are the absolute most important things when it comes to defining the shape of our flight number data. And for a launch date, I will likewise say that the type is a date. And of course, each launch needs to be scheduled for some date, so we'll say that's required as well. Let's see, what else do we have? We have missions and rockets. Those are both going to be strings, so we can say mission, type, string, and that's required as well. And we have rockets, also strings, and also required. And let's make sure to use the right type, so it needs to be string and not strings. But here's where we get interesting. Our next property is this target, which refers to a planet, which is going to have its own schema because we'll be storing planets in their own Mongo collection. As we discussed earlier, using a SQL database, we would reference a target planet by using what SQL calls a foreign key and assigning only the ID of the target planet in our launch. And it would be the target planet that lives in the planets collection, in the planets table, that would actually store the data for our planet. In this case, the name. And Mongoose actually supports a similar approach. We could say that a target references a planet in our planets collection. This would look something like this. We would say that our target is a reference pointing to a planet, and that its type is this property from our Mongoose package called mongoose.objectID. This ID would allow us to look up planets from that planets collection. When creating new launches, Mongoose would now check and verify that any planet we reference in our launch is actually one of the planets in our planets collection in Mongo. And we'll learn a lot more about this object ID as we continue learning about Mongo. But the truth is, this approach with references actually ends up making our life with Mongoose a lot more difficult. Mongo doesn't support features of SQL that make this approach work. In SQL, we have what we call joins, which make it easy to combine the data from one table with the data in another table, like launches and planets. Because Mongo doesn't support these joins, we'd have to code all that logic ourselves and essentially recreate part of what a SQL database would do. This wouldn't be very easy to do well at all. Databases are highly specialized pieces of software that have been perfected over decades. So instead of adding all of this complexity, with Mongo, we generally want to take a different approach. It's the NoSQL approach, where we include the relevant data from our planet directly in our launch, directly in this target property. So no extra lookups are required. All of the data that we're interested in lives in this collection. What does this look like? Well, the data from our planet that we actually care about is just the name, which is a string. So we'll just store the string, including the name of our planet, as the target. And we can say that, of course, every launch needs to be targeting something, so we'll say that's required as well. All right, and we have the upcoming and success properties. So we'll say upcoming is a Boolean. And you know what? I think most of our properties are actually required. So we'll say we need to say whether this launch is coming up in the future or has already happened. And for success, we'll say that's a Boolean. Also required. But this time, remember we're optimists, and our launches start out as a success. It's only marked as not a success if something goes wrong or we abort our launch. So we can take advantage of this default schema property and set that to true. Now, if we don't pass in a success property, one will be set to true. And if you're paying really close attention, you'll notice that I skipped over the customer field. This is an array of strings. Sounds like it could be complicated? Well, not really. We can add customers, and I'll make it customers with an S because we use customers in the plural form when we add our new launch. So let's be consistent everywhere. I'll update this to say customers. And in our schemas, we can say that this property is an array of strings. Just like that, using the array square brackets. I'll close out this with a semicolon, and that's it. We have our first sample Mongoose schema. But a schema isn't very valuable just on its own. We need to apply it when querying documents, and we need to create some launches in the first place. So let's keep going, and we'll see Mongo in all of its glory as we progress through this section. I'll see you in the next one. All right, we've made a schema for our launches that we're pretty happy with. Now it's your turn. How should the schema for our planets collection look? Beside our launches.mongo.js file, we'll create planets.mongo.js. This one will be a fair bit shorter than our launches schema. We know our planets will contain a planet name, and just a name. Think about the data type. Is the data required? Are there any reasonable defaults? And are there any other restrictions on the planet name? Use the launches schema that we just created as a reference. And when you're done, let's continue with this video and review our work in making our schema in planets.mongo.js. All right, have you had a chance to make the schema? Let's compare our solutions. To create a Mongo schema, just like before, we need to require mongoose and set it to a constant. So we'll say const mongoose equals require mongoose. All right, that's the easy part. Now we'll create our planet's schema, planet schema, and assign it to a new mongoose.schema object. Remember, we pass in our schema as this set of properties, which each have, at the bare minimum, a type associated with them. What do we want to name the property on the planet schema? We're storing the planet name, so you could have chosen anything like name, or planet name, Kepler name, or something similar. If we really wanted to look ahead and make our lives easier for the future when we integrate with the front end, ideally, we want the name of our planet in MongoDB to follow the same naming convention that we use in our client in the front end under source, pages, and where do we use the list of planets? When we select the target planet as we're scheduling our mission launch. Here, where we create our selector body, which is the list of planets that's listed under destination exoplanet, we use this Kepler underscore name property from our planet. So whatever field we have here is the name that we want to use in our planet's schema when we name the property for each of our target planets. So I'm going to change this, and we're going to use the camel case convention throughout our code. We want to be consistent in our naming rather than using the words Kepler and name separated by an underscore, which we call snake case. We'll capitalize the second word and write Kepler name in camel case, both when we set the value here and in the key, as well as in the content, in the text that shows up for this selector item. So we're using Kepler name in camel case in our launch.js file on our front end, which means that now in our schema, we can use the camel case version as well. We're just making our life easier so we don't have to keep renaming this property as we pass it around between the backend and the front end. So our Kepler name, the name of our Kepler planet, is going to be type, that's right, string. And because this is the only property that we're storing, it's definitely required. So we'll say required true. And is there anything else? Can we set a default planet name? Well, there's nothing that would really make sense because we can't predict planet names, which means the amount of validation we can do here is pretty limited. We're happy with taking just about any string as the name of our planet, which means if we punctuate our file with a semicolon, our planet schema is ready. All right, in the next video, let's take the schemas that we've built and start applying them to make some queries to our Mongo database. It's gonna be a fun one, so I'll see you really soon. Welcome back. It's no fun writing code without being able to run it and see it in action. To put our shiny new Mongo schemas to use, we need to connect them to a collection in our Mongo database. A schema is only useful when it's mapped to collections of documents inside of our MongoDB. This step is a quick one. We map our schemas to collections by using Mongoose models. Let me demonstrate. Take the launches schema that we built. We constructed a new mongoose.schema object and assigned it to launches schema. We can now create a model with this schema by, below where we've created our schema, calling mongoose.model, typing in the name of our collection. I'm going to say launch, and as the second argument, we pass in the schema that we just built. So launches schema is assigned to the launch collection. This first argument here should always be the singular name of the collection that this model represents. Mongoose will then take what you pass in, lowercase it, make it plural, and talk to the collection with that lowercase pluralized name. So our model down here connects launches schema with the launches collection. And launches is written exactly like that. This is because MongoDB collections should always be plural nouns. They represent potentially many launch documents. When a model is set to use a schema like this, Mongoose calls this statement compiling the model. But basically, what we've done is we've created an object which will now allow us to create and read documents in our launches collection. We'll use this Mongoose model by exporting it from this module. So we'll set module.exports to be this Mongoose model, which means that we can now, inside of, say, our launches model, we can require this mongoose model, this representation of our launches, by saying const launches equals require dot slash launches dot mongo. That's the file with our schema and the model which compiled that schema. Now, we now have two launches in this file, so I'm going to comment out our require statement for now, and we'll circle back to this very shortly. First, let's create a model for our planet schema. Do you remember what we did? We called mongoose.model, passing in the name of our collection in the singular form. So we'll say planet, and then passing in our schema as the second argument, planet schema. With this compiled model, we can now export module.export our object, which will allow us to perform actions in our Mongo database. And there we have it. We're about wrapping up the setup, and we'll get to the fun queries in just a bit. All of this build-up will be worth it. I'll see you in the next video. Welcome back. We have these mongoose models in our .mongo files, where we compiled a mongoose schema and assigned it to a collection in MongoDB. But we also have these model view controller models in these .model.js files. This was confusing to me when I started working with Mongoose. I mean, why do we have two models? Isn't one enough? Before things get out of hand, I'd like to clear up any confusion around these two different models. Our mongoose models are not exactly the same as our models from the model view controller design pattern. Models and schemas are objects and classes that Mongoose provides for us to talk to collections of documents in MongoDB. These are very specific tools, while models in Model View Controller are a more general concept that can apply to any database or any external data source. Our model is something that generally captures the data our API is working with. Now, in some Node projects, you'll see just one model. You'll have a model.js file, which most likely just exports the mongoose model that we have here directly. So why do we have these additional models in our NASA project? We're using these model files here to act as the data access layer that controls how data is read and updated, while hiding the Mongoose and MongoDB specific implementation details, the things that are in our mongo.js file. If we ever decided to switch databases, we could swap out the implementation of our model here to use a different data structure or database. Because our controllers only work with the functions that we export from this file, and they don't care about how they're implemented, none of the code in our controllers or any of the code above this data access layer will have to change because of how we've set things up. At least, any changes would be limited to the overall higher level functionality that our model supports. Allowing for this kind of flexibility is a big part of what these extra layers and abstractions are all about. Our model.js files here are higher level and easier to work with in the context of what our API is trying to do than a Mongo or Mongoose model would be directly. I hope that can help clarify to you why it might make sense to not just use the Mongoose model directly as the model in our API project. Not if we're making a large project that we're going to maintain for quite some time. With that out of the way, let's save some data in Mongo. I'll see you in the next one. Welcome back. In this video, we're going to populate the planets collection in MongoDB with the list of habitable planets. Those same planets that we found in our Kepler data. The code here that works with our planets data lives in our planets model. Right here under source, models, planets.model.js. The planet finding logic won't change. The part that will change is this habitable planets array and how we save and push data that's currently being stored in memory, but that we instead want to persist forever in MongoDB. As we make changes to our model here, we're going to try to do so without breaking our server all at once. We want to be able to test each of our changes as we make them. So we're going to leave some of the in-memory objects storing our planets, for example, or our launches, while we move them over to Mongo. This is just a temporary step during development so we can do things incrementally, step by step. A common mistake that new developers make is trying to change too many things all at once, finding themselves in a hopeless situation of the new approach not working and the old approach not working either. The best way to avoid this is to break things down into the smallest possible changes, just like we do in these videos. We want to take things step by step, so let's take the very first step. We're going to use our planets Mongoose model over here to insert the planets that we find into our planets collection. So let's take that Mongoose model and require it. Right here below our built-in imports, we'll say const planets equals require from the same folder, planets.mongo.js. And as we mentioned, we're going to keep the in-memory storage, which is called habitable planets, around just for now. What we want to do is, after our planets data is parsed and read from our Kepler data.csv file, when we detect that a planet is indeed habitable, we're going to save it not to our habitable planets array with this push function, so we can remove that, but instead to MongoDB, which we can do using our planets model that includes many functions for us to find documents in our planets collection, to remove documents, and also to create new documents by passing in the planet data that we want to save. The same JSON data that will be saved as a document in our Mongo collection. And as with every Mongoose operation, whether we're creating, reading, updating, or deleting documents, we can await the result, because our create operation is asynchronous. It's Mongo that's responsible for storing our data and not JavaScript. So that means we need to make our callback function here asynchronous. But now remember, our planets collection is using the planet schema that we defined just a short while ago. And the planet schema requires that this Kepler name property is set and doesn't really care about the rest of the planet data. Which means when we create an object, a document, with our create function here, we need to pass in the data in a way that matches that schema. Otherwise, our document won't be saved. So rather than passing data in directly, what we'll do is we'll create an object which matches the shape specified in our schema, where Kepler name, in camel case, matches data dot Kepler underscore name, which is the name of the column that corresponds to the name of our planet from our Kepler data.csv file. So now, our document should be created. But let's think about this for a second. We're creating all of these planets when they're matched as habitable every time that we call this load planets data function. And this function is exported from our planets model and called in our server.js when we start the server. So if we restart the server or run many instances of the server in, say, a cluster, we're going to be calling that load planets data function many times and duplicating all of these documents that we create in our database. Luckily, Mongoose makes it easy for us to solve this problem. We can use what's known as an upsert operation, where upsert is just a combination of the words for insert plus update. That's upsert. So how does this upsert help us? Well, an upsert is basically just an insert. Just like our create operation here inserts the document that we pass in. But the update part allows us to insert only when the object that we're trying to insert doesn't already exist. Sounds pretty great, right? How do we upsert with Mongoose? Well, here's the thing. To best understand how upsert works, it'll help to understand how the find operation works in Mongo. Let's learn about find in the next video and then circle back to replace our create statement with an upsert. For now, we don't want to create a bunch of duplicated data in Mongo, so let's comment this out for now and give ourselves a to-do here saying replace below create with insert plus update, which is our upsert operation. Let's learn all about finding documents in MongoDB. I'll see you in the next one. Welcome back. You're still with me? Awesome. Here's the plan. We're going to build out our planets controller right here under routes, planets, planets.controller.js, where we get the list of all habitable planets. This is going to use the Mongo find operation, which we'll learn how to use with our Mongoose package. And after we've done all this, we're going to come back to our planets model, where we save our planets and use our upsert operation to make sure that all our planets are saved only once. Sounds good? All right, let's go. Starting from our planet's controller, we can see that we list all of the planets by using this getAllPlanets function in our planets model, right here at the bottom of our file. The list of planets returned from this function is what is shown in the destination planets selector in the front end. Here's a little reminder of what we're working towards. Because we're now using Mongo, rather than returning this habitable planets array, we're going to be using the planets mongoose model that we require from our planets.mongo.js file, and we're going to be using some operation on this planet's model. We've already seen that with our planets, we can call create to add new documents to our collection, and we also have these find operations, where we can either find many documents, or we can restrict our operation to return only at most one document. So we want a list of planets, which means we'll be calling find, and this operation allows us to pass in a filter which will determine which planets are returned, which documents Mongo should find for us. Our filter takes the form of a JavaScript object. If we pass in an empty object, all documents will be returned. But if we passed in, say, a Kepler name, maybe Kepler-62f, only documents matching those properties would be returned. And our find operation takes a second argument, also an object, which is what Mongo calls the projection. It's the list of fields from those planet documents that you'd like to include in the result. This can take one of two forms. Say we wanted to include only the Kepler name field, we could pass in this object with the Kepler name set to 1. This would show the Kepler name field. If we set it to 0, it would exclude the name from our returned documents. Now, Mongoose gives us another option where we can pass in a string directly as this projection with the list of fields we want to include. So Kepler name, and then if there was another field, we could include that followed by a space, another field. Now, if we wanted to include only another field and exclude Kepler name, we could add a minus symbol in front of the field that we want to exclude. The find operation is a powerful tool, and we can learn more about it in the Mongoose docs under API, model, because we're calling find on our models, and if we scroll down here, we'll find model.find. Notice the filter and the projection. Find also lets us use these operators such as greater than or equal to, or less than or equal to. That would be $LTE to look for ranges of numbers. Or we can use regular expressions to match strings, like matching all names that include the name John. Find gives us many options. Luckily for us, the getAllPlanets query is going to be fairly simple. To start, we're happy getting all of the fields in our object, and we're not looking for any specific planet. We're looking for all of them. So we'll pass in this empty object as the filter, and we'll remove the projection. Now, because our Mongoose operations are asynchronous, we can't forget to await our planets.find operation and make our getAllPlanets function async, just like that, which means that our controller now needs to be async as well, because HTTP getAllPlanets, our async function here, is going to be awaiting the result of getAllPlanets, just like that. Now we can run our server. I'm already watching the server folder for changes, just to make sure that everything's working, and, well, there's not much to see because we're not populating our list of habitable planets. Now that we know how the find operation works, let's get back to that upsert. It's going to be a good one, so let's go. Let's finally populate our planets collection. In our planets model, when we load our planets data, we could call this create function to insert the planets documents into our planets collection. But remember why we wanted to upsert? We want to make sure our planets are only added if they don't already exist in our database. Because our load planets data function here could be called multiple times. Okay, so let's take a step back here. What exactly is an upsert? Well, an upsert inserts data into a collection if it doesn't already exist in that collection. And if that document does exist, then it updates that document with whatever you pass into the upsert operation. What does this look like? Well, let's uncomment our create function, but this time we'll replace create with this mongoose update, and we can see that mongoose lets us update many documents or restrict our operation to just update one document. That's the one we want because we're just inserting one planet, as long as it doesn't already exist. And the update one function, just like our find operation, takes a filter, a query, as its first argument. So what we're doing here is we're finding all of the documents with a Kepler name that matches the Kepler name from that CSV file that we loaded and that we're parsing in our load planets function. Okay, so we're finding all of the planets with a name matching the current planet. That's to make sure that we're only inserting planets that don't already exist. And if it doesn't already exist, the object we're inserting is the second argument here. And if it does already exist, then we'll just update that document with whatever's in this second object. So in either case, we'll just pass in that same Kepler name with the data from our CSV file, Kepler_name. And now, by default, our update one function will only update if this planet doesn't already exist. It won't do anything. That's where our upsert comes in. If we pass in this third argument here, and we set upsert to true, well, now we finally have our upsert operation. Our planet will only be added if it doesn't already exist. And if it does, well, our update over here won't change anything. So we're ready. We've done what we've came here to do, so we can replace that and remove it. But we can do a little bit better. We're in a model, which means we want to create these reusable data access functions like when we get all the planets, that abstract away all of the Mongoose-specific functionality and create these more reusable functions. So let's do that for our code over here, where we save one of our planets to Mongo. I'll move this out of our if block and create an async function below getAllPlanets to save our planet, taking in some planet data and calling our update1 function on that planet data. So let's replace data over here with planet. Oh, and we have to make this a function. And now that our Mongoose functionality is captured by this savePlanet function, we can call it when we have a habitable planet, passing in the data from our CSV file. Now, what about errors? What happens when our update1 function fails to save the data and something went wrong on the Mongo side? In our database, it's possible that this update1 function will throw an error, which means that we should probably wrap it in a try catch block. So let's move our update1 function into the try and catch any errors that are thrown, where we'll just say console.error, saying that we could not save a planet, and we'll include the error in our template string. So I'll say $error so that the user knows exactly what went wrong. Let's check our work. We should be getting our 8 habitable planets found, but right now only 0 are being reported as found. What's up with that? Well, in our loadPlanets function, we're still checking the length of our habitable planets array over here. So you know what? Let's finally get rid of this habitable planets array and make sure that we're only using our Mongo database as the source of truth for our planets. To get the amount of planets in our habitable planets collection in Mongo, we can create a variable, a constant called count planets found. And what we'll do is we'll just call getAllPlanets and check the length of the array that's returned from planets.find. So what we'll do is await getAllPlanets, and now we can wrap this all in parentheses and call .length on the resulting array. Now, hopefully, if we print out the count planets found constant, we'll get our 8 planets. Oops, looks like something went wrong. Unexpected identifier, because I'm calling await, and that means I need to make our callback function here async. Let's try again. There we go, 8 habitable planets found. And if we load our server on port 8000, let's see if our list of planets is available in our NASA dashboard. When our front end's loaded, check it out. We have all 8 planets available as potential targets for our interstellar launches. Very nice. Welcome back. How can we explore our Mongo database without using Mongoose? If we make a mistake when creating our data, how do we fix it? Say we ended up duplicating the amount of planets that we save. And now in our front end, it's showing each Kepler planet multiple times. We have to remember that our data is now being persisted. If we want to start from scratch and fix our mistakes, one option we have is to go into our MongoDB Atlas and manage our data from here. From our cluster dashboard, we can click on our cluster and go under Collections and Atlas will show us the name of our database that we created. Remember, we connected to the NASA database and we created a planets collection. We haven't added any launches yet, so we only have this one planets collection. So if we click on that collection, over here on the right, we can see the information for that collection, its size, and the amount of documents that we have. Notice that we have twice as many planet documents as we expect. And we can see that each of our documents has not just the Kepler name that we assigned to it, but also this ID and __v properties. We'll get to these object IDs and the __v in just a bit. But for now, we want to fix our mistake. And so if we wanted to, we could go into each of these documents and edit them manually. I can write whatever I'd like for my planet name here, Adam's home planet. And I could update that in the database. Or I could delete individual documents. But in this case, I'm fine with just clearing the entire planets collection and starting from scratch. After all, the code in our API populates all the planets that we need. So I'll remove the planets collection. I may need to type a confirmation. I'll drop that. And now with our collection removed, if I restart the server so that the load planets data function gets called again, let me do that. I'll clear the terminal and run npm run server. We get our planets being found. And now back in our database, if we refresh, check it out. Our planets collection is back to how it should be. 8 documents found. And if we go back to our NASA front end and refresh that, let's see what planets are listed. There we go. Problem solved. Before you go, I'd like to leave you with just one tip. We can do a lot from our Atlas dashboard. For example, here in this field under our planets collection, we can run any of our find queries that we discussed. Remember, we could filter our documents by passing in the name of a property, something like Kepler name, and maybe we want to match Kepler-62f. If we run that find query, we get only the documents that match. Very useful if working with larger collections of data and we want to quickly explore our Mongo cluster. All right, I'll see you in the next one. Welcome back. You haven't forgotten about our architecture diagram, have you? In this section, we've added a very important piece to our project architecture, our Mongo database, and the cluster that we're hosting on MongoDB's Atlas service. Let's add that database right here, and we'll use the solid line and a new color because our database is a core component of our architecture that deserves its own category. So let's just say that our database is in this shade of red right here. We'll be very clear that this is a MongoDB cluster, and we can make this look nice by creating a few copies that will move to the background. So I'll move this first database icon all the way to the front, and I'll remove the labels from the ones behind. And I can rearrange this a little bit. I think I like it better below, right here. There we go. That looks perfect. Our MongoDB cluster is a separate part of our project that we manage separately from our code in the NASA project npm package. So let's add a box to capture the database and what's hosted on MongoDB's atlas. I'll move this to the back and label it as MongoDB atlas. And our database is called NASA. So I'll say NASA database. Let's give this the correct color. And there we have it. Now we know that our database is hosted on Mongo's Atlas service, and we can add a connection between that cluster and, well, what does it talk to? It talks to our Node API. Let's clean things up a little bit and rearrange our NASA project section here to give ourselves a little bit more room to connect to any external services. So I'll move this CSV file over just a little bit. I'll connect it over here. And now I can make this box a little bit smaller because we won't be downloading many files manually and storing them on our server. But we will be talking to many different cloud services. So for now, I'll move the cloud services that we do have over here closer to our project. The manual download applies to our exoplanet archive. And now it's very easy for us to connect the MongoDB cluster with our Node API using our solid line, because we're talking to Mongo in an automated way using Mongoose and the MongoDB driver. So let's label that. We'll say that we're using Mongoose, MongoDB driver. And actually, the implementation detail of Mongoose isn't important when it comes to our project architecture. What's important is that we're using the official Mongo driver when talking to MongoDB. We're connecting to our Mongo cluster using that MongoDB protocol that our driver uses to communicate with our database. And this is important. The connection with our MongoDB cluster is bidirectional. We get data coming in from our cluster, but we also populate the data for our planets and launches collections. So let's add an arrow at both sides. And there you go. That's our updated mission control architecture in a nutshell. I'll see you in the next video. Welcome back. What are object IDs in MongoDB? When using Mongo, you'll see these object IDs being referenced all over the place. For example, say I'm in Postman, and I make a GET request to the planet's endpoint in our server. What comes back? Let's see. We get not only the Kepler names of the planets that we've marked as habitable, but also these _ID properties and __v. These are values that are automatically created in Mongo whenever you create a document. This ID property is what's known as an object ID, which is how Mongo identifies documents uniquely. At its core, this object ID is a random-like value that's assigned to the document that will always be unique to that document. It uses these long random values as opposed to an ID that auto-increments, like 1, 2, 3, and so on. Because remember, Mongo is designed to be run in a horizontally scalable way, in a cluster with many instances of the Mongo process. This ID needs to be unique across all instances of the database in that cluster. We don't want an object or a document that's created in one instance of Mongo to match up with the ID for a document that's created in another instance, because then when we query that cluster, we'll get two different objects with the same ID. So the object ID is Mongo's way of making sure that these IDs are always unique to each document. It's very, very unlikely that two different documents will have the same ID. If I take this ID right here and copy it, we can actually see that this ID isn't truly random, but it contains a random value, but also the date that this object was created. In my browser, if I search for object ID to date, there's a few of these Mongo object ID to timestamp calculators that we can find online. I'll attach the link to this video. But if we paste the object ID that we just got from Postman, we can see the date and time that this particular document was created from this seemingly random value that is our object ID. In Mongo, there's no need to save the creation date of your documents because that's built in to how Mongo stores object IDs. Pretty cool, right? Let's keep going in the next video. Welcome back. We've learned about these object IDs, but what about this __v value? This isn't something that MongoDB itself creates, but it's an added advanced feature from Mongoose. Mongoose adds this property that it calls the version key to help keep track of the version of the document that you create. What is this used for? If you change the schema of your collection, say our planets collection, but you want to keep the old data around, the data that follows older versions of your schema, you can increase the __v value of your new documents to show that you're using the newer version of your schema. This is one great way to take advantage of Mongo's so-called schemaless approach. You can potentially have documents that follow different versions of your schema and your database won't break. It would be up to your application code how to manage documents with each version of the schema. Pretty powerful stuff and much more flexible than the equivalent in a SQL database, where you'd have to do a complicated database migration, which would likely bring your database down for some period of time. All right, So these object IDs and version keys have their important uses. But we're talking about our API. We're not always interested in these internal values when we return the planet's data in our endpoints. That's totally fine. In fact, it's a good idea to filter out these internal values when we return the documents in our API. When we get all the planets in our planets model, remember we're using this find function, which allows us to filter documents based on some criteria. That's the first argument. But the second argument here, the so-called projection, allows us to select which fields are included in the response. So we can say, if we want to exclude the ID and the version tag and the version key, we can write __ v and set that to 0, and also set _ID to 0 as well. We're telling our find operation to specifically exclude properties which match these names. Now with our server reloaded, if we make our request in Postman again, check it out. We're getting just the data that we're interested in. Much better. Welcome back. We've learned enough about MongoDB now to be an expert when the topic comes up. Let's put this newfound knowledge to use to save newly scheduled launches to our database. Let's start by adding the capability to add a launch, like our example here, to MongoDB. We're going to be using our launches model that connects our launches schema over here to the corresponding collection in MongoDB. So we'll take this export here, and in our model.js file, we're going to replace this call to launches.set, which is a function on our map, our in-memory store here, with a save launch function that talks to MongoDB instead. So down here, below get all launches, let's create a function to save that launch. It'll take in our launch data. And basically what we want to do is take an object like we have here and insert it into our launches collection. But if a launch with the flight number that we pass in already exists, we'll just update the launch with that ID with the values that we pass in to our save function. Does that sound familiar? That's our upsert operation. So how does upsert apply to our save launch function here? Well, remember our Mongoose operations are async, so we need to make our save launch async, which means we can now await launches, which is how we imported our launches.mongo.js file. And we're going to be calling that same update1 function that we called when we created our planets. Because we're saying that our save launch function here will only ever save one launch at a time, and not many, which would be the update many function. All right, so we're updating one, and remember this first parameter here is how we're finding if this launch already exists in our database, which we already agreed was determined by the flight number of that launch. So we're checking if the flight number, which matches this new launch's flight number, so launch.flight number, if that document already exists, then we're just going to update, and if it doesn't exist, we'll insert. And what are we inserting? Well, we're inserting the launch object. That's the second parameter here to our update1 function. And because we're doing an upsert, we need to remember to pass in this upsert option as the third argument. So we'll say upsert true inside of this object. All right, looks good. Let's call this saveLaunch function on our sample launch that we built right here. We're going to say saveLaunch, passing in that launch object. And we'll remove the old code that used our map. Do you think this works? Well, our server is crashing, so we need to fix that. Launches has already been declared. Let's take a look. We need to get rid of our old map or name our import something that doesn't conflict with the old name. Because we don't want to break our old code just yet, let's rename launches to launches database. And in our saveLaunch function over here, we'll call update1 on launches database. All right. If we run our server again, it looks like our code works. But to really see if our launches are being added to Mongo, we're going to need to implement this getAllLaunches function, which will let us use our API to get feedback on whether our code is working. Let's find out how to list all launches in the next video. Welcome back. Our getAllLaunches function here should list all of the launches that we've persisted in our database. This is the function that gets called in our launches router when we get the launches collection in our HTTP getAllLaunches controller function. Let's implement this function so that we can get feedback from our API that we're adding launches as we expect. Rather than using our launches map, our pattern has been to use this launches database that we get from our Mongoose model connected to our schema. To get some documents from Mongo, what we'll do is call the find function. And again, this is an async function, so we'll await the response and make our getAllLaunches function async as well. What do we pass in as the filter in our find function? Well, we'll pass in just the empty object, which is Mongo's way of saying that we want to find all the documents in our launches collection inside of our database. And this time, we'll use this projection argument to make sure that we're not showing the MongoDB ID or the Mongoose version key in our response. So let me move this .find one line below. And now inside of this second argument, just like with our planets, I can set the underscore ID, which stores the object ID, to 0 to exclude that from the result, and also set underscore underscore v to 0 to exclude Mongoose's version key. Now, when we call our getAllLaunches function in our controller, we need to make sure that's async as well. And we'll await the result when we call getAllLaunches. Let's test our work. We should be creating one launch that matches this sample when we start our server up. So in Postman, if we call our getLaunches endpoint, there we go. Our sample flight with flight number 100 is being returned. That was a short one, so let's keep it going. I'll see you in the next video. Welcome back. We now have the ability to list all the launches that we've saved in Mongo. Great stuff. But there's something strange here. We have a list of planets that's also been saved in our database. These are the planets that we want our launches to target. But what happens if we create a launch targeting a planet that's not in our planets collection? What if we save a launch that's targeting not Kepler 442b, but instead Adam's home planet? Will this work? Well, there's nothing in our save launch function that prevents that document from being created. In fact, if I save this file and go into Postman, I can now get the list of launches, and our sample launch is targeting that mysterious planet, which I assure you is Earth. But we're now targeting a planet that doesn't exist in our database. This wouldn't be a problem in a SQL database. One of the great things that SQL gives us is what's formally called referential integrity. When you reference a value from one table in another table using what SQL calls a foreign key, say you're referencing an artist by their artist ID from another table that lists the album names for that artist. SQL will make sure that the value in the table you're referencing, say the artists table, actually exists. SQL will prevent you from referencing an artist with an ID that isn't saved in your database. Notice artist with ID 4 doesn't exist in our table, so a SQL database wouldn't allow you to insert this row into the table. That's what we want for our launch data. Where we reference a target planet, we want it to match only the planets in our planets collection. We want to make sure that the target planet exists in our database and has been officially marked as habitable. If that planet doesn't exist, well, that's an invalid launch. Unfortunately, MongoDB isn't quite as good with enforcing this idea of referential integrity as SQL databases are. However, if we want to validate that the launch that we're saving is actually referencing a valid planet, there's a few approaches that we can take. The simplest approach is to add some validation before we update our launches database to check if the launch target planet exists in the planets collection. So we can do this by requiring our planets mongoose model here by doing const planets equals require /planets.mongo, just like we're requiring our launches, and using this planets constant to find the corresponding planet and verify that it exists. Notice that we're importing the planets.mongo file and not planets.model.js. We could add a function to our planets model that checks if a certain planet exists in our database, the MVC model in our model.js file. But in general, when we're at some layer in our code, right now we're in the data access layer in our model.js file, we want to talk to files that are in a layer below our current layer. This is so that the web of dependencies between each of our modules and files doesn't get all tangled up, causing more issues down the line. I know that sounds a bit abstract, but basically, because we're talking to our launches.mongo file, it makes a lot of sense for us to also talk to our planets.mongo file and not mix and match. The pattern here is that our model.js files talk to these .mongo files. All right, so what are we going to do with our planets? Well, in our saveLaunch function, we're going to find that planet. We can assign it to this constant called planet, and we'll call the planets.find function, which we can await from our async function here. But find returns many documents all at once. It returns a list of the documents that match whatever filter you pass in. In our case, we know that there's only ever going to be one matching planet that we care about if it indeed exists in our database. So we can call this find_one function, which just returns the JavaScript object and not a list. And the JavaScript object that we want is the one matching the Kepler name from our launch, the one marked in our launch.target. With the result from this find operation, we can check if this launch target planet doesn't exist in our database. So if no planet was found, what do we want to do? We're in our data access layer here, and not in a controller where we might have access to the request and response objects, which we could use to immediately send an error back to the requesting client. We're in a lower layer of our API. Here, how we signal errors is either by returning invalid objects, like null or undefined, or preferably, by throwing errors. For example, if no planet was found, we'll throw a new error using the built-in node error class, and we'll pass in a message saying that no matching planet was found. If we view this list of node best practices on GitHub, which I'll link to in this video, and we scroll down under error handling practices to the second item here, notice that it tells us use only the built-in error object. We don't want to use some custom type, as that can complicate the error handling logic by just adding a special case when we try to handle that error. Instead, we want to try to keep things uniform so that errors can always be handled in a predictable way. And when we use the built-in error object, we want to always call the new keyword when creating new errors, to make it clear that we're creating a new instance of an error object. Now, when no planet matching our launch target is found, our saveLaunch function will throw an error wherever it's called. For example, when we add our sample launch. So if we try to add a launch with Adam's home planet, our saveLaunch function should throw an error. Is this what actually happens? Let's see. If we open our terminal and scroll up slightly, node is telling us that no matching planet was found. An error was thrown inside the saveLaunch function. And if we change our target planet to something in our list of habitable planets, say my favorite exoplanet, Kepler-442b, and save that, let's reload our server, and no error. Now if we go to Postman, there's Kepler-442b in our list of planets, and if we get our launches, we should now see a valid launch targeting the planet that we just set. Very nice. Just like we originally wanted, we're now maintaining that referential integrity and checking that our target planets exist in our database. We've covered a lot of topics in this video, so pat yourself on the back. And in the next video, we'll put everything together to schedule real-life launches. Well, kind of real life. You know what I mean. I'll see you in the next one. Welcome back. This is going to be a good one. We're going to look at a common feature in SQL databases and see how we might accomplish the same thing in MongoDB. What have we already accomplished? Our launches model can now create new launches in our database by calling the saveLaunch function, and we can also get all of the launches in our database. That means we now have the pieces in place to start looking at scheduling new launches. That's what we were doing in our add new launch function when we were using the launches map. This built-in launches JavaScript map object. The general idea of what we want to accomplish is when we schedule a new launch, we want to first, of course, save it to our database and increase the latest flight number by 1. If we scroll up to where latest flight number is defined, with our in-memory approach here, we actually had 2 pieces of state that our API was tracking. We had the launches map, but also the latest flight number. To make our API truly stateless, we need to move all of the state to the database, including this latest flight number. Remember, we're persisting our data to an external Mongo database so that our node process over here doesn't need to track anything in its memory. If we're running our node processes in a cluster, we want to be able to handle our requests in any of our node processes and get the exact same behavior using the exact same state. And we accomplish that by getting any state that this request needs from an external database, from something that doesn't live inside the memory of our node process. The truth is, unfortunately, one of the things that is much more difficult in MongoDB than in SQL languages is the management of numbers like our latest flight number that we want to automatically increment when we add new launches. For all the benefits that Mongo gives us, like using JSON objects everywhere, letting us scale our database horizontally, and giving us flexible schemas, these automatically incrementing numbers are unfortunately one of the downsides. In SQL, we could just use this auto-increment feature that's included in pretty much every SQL database. Right now, as an example, I'm looking at the MySQL documentation. Let's see. When we define our schema in SQL, which you can see here with the create table command, this creates a rigid structure for our table. In this example, we have a table of animals that contains a name and an ID. And using this auto-increment feature, we're saying that the ID is an integer. That's the int part here. The ID is basically a number that automatically increments by 1 every time you create a new animal. SQL itself manages that ID and what its next value should be. That's exactly what we want for our flight number. if you're using Postgres instead of MySQL, similar to the auto-increment property, Postgres uses this serial feature, which does pretty much the same thing. However, if you look up MongoDB auto-increment in Google, you'll see thousands and thousands of questions and tutorials on how to duplicate this basic functionality. I can summarize all of these articles by saying that each approach is fairly complicated if you look at all of the different possibilities for what can happen. There are ways in MongoDB to auto-increment a number, but that's just not the Mongo way. So what is the Mongo way? Why is it so difficult to auto-increment a number? The reason comes from one of Mongo's big strengths, which is that it's very easy to run a cluster of Mongo databases where you horizontally scale Mongo, not just by having one instance of it, which you talk to with your server, but instead your server talks to potentially many Mongo databases that are tied together into a cluster, each sharing the load for part of your queries. When you have many databases running side by side, which one decides to increment the counter? Which one stores that state? It's not an easy question to answer. Maybe all of the database instances should keep track of that number. But then we need to keep that number in sync with all the databases whenever it increments. And that adds additional complexity. This is complexity that the Mongo developers didn't really want to deal with. They had something else in mind. The Mongo approach sidesteps this issue and does things in a way that doesn't need this auto-increment feature, in a way that still lets you build these really performant Mongo databases. As with anything, the ability to scale our database horizontally and run a cluster has come with the additional cost of complicating a few basic operations. Luckily, the Mongo approach to solving this problem makes a lot of sense and won't be too hard to implement. Now that we're aware of one of the trade-offs that we make when we use MongoDB, let's solve our auto-increment problem. I'll see you in the next one. Welcome back. We need to keep track of our latest flight number and increment it by 1 every time that we schedule a new flight or a new mission launch. What's the best way of doing this? One approach that simplifies things is to store our launches as normal and figure out the latest flight number as a separate step. Just like with any problem, we're going to break it down into a smaller problem that's easier to solve. So how do we figure out the latest flight number? Let's make a new function right here above getAllLaunches that we'll call a function called getLatestFlightNumber. We're going to make our function async because it's going to be querying MongoDB. We're going to get the latest flight number that already exists in our launches collection. And we're going to use that instead of this latest flight number that's stored in memory. So we can remove this variable, and instead, in our function, what we'll do is we'll get the latest launch as a constant by awaiting the result of a query on our launches collection, which we can access with the Mongoose model that's stored in launches database. We'll start by finding the launch with the highest flight number. So we're going to be calling the find operation on our launches database, and we could pass in some filter into our find query. But remember, our find operation returns a list of documents that matches our filter. In our case, we just want to find one document that has the latest flight number. We're going to be a little bit clever here, and we're going to get the latest flight number by sorting the documents in our launches collection, which we can do by adding this call to the .sort function that Mongoose makes available to us. This takes advantage of Mongo's built-in sorting capabilities. And because we're finding one document, we don't need to pass in a filter, but we do need to pass in some criteria to sort by. The criteria is that we want to sort by a property, which we can pass in as a string, and our property is flight number. Right? If we look in our launches schema here, we store the flight number under that property name. So in our model, passing in the property will sort the documents by that property in ascending order, from lowest to highest. And what find one will do is it will return the first document if there's more than one that's returned. So we're taking all of the launches, we're sorting them, and then we're taking the first one in the list that's returned. Which means to get the latest launch, we need to sort in descending order, from highest flight number to lowest, which luckily is a matter of just adding this minus in front of the property name. Now our latest launch will be the one document with the highest flight number, the topmost document in the list of launches sorted in descending order. All right, so we have the latest launch, and we want to return from our function that launch's flight number. So we can return latest launch dot flight number. Just like that. There is one case we need to consider here, which is if there are no launches in our database, we still need to be able to save that very first launch. So we can check if there is no latest launch. So if that value is null, if not latest launch, then what do we return as the latest flight number? Well, we can create a constant up here at the top of our file. Say we'll call it the const default flight number. This is the first flight number that will be assigned. We could set this to 0 or any number we'd like. Let's say 100. And now if we return this when there's no launches, so return default flight number, our launches will start from 100. Very nice. Let's use this function that we've just created to schedule new launches through our API. We've built up all the pieces, and now we're going to put them all together. I'll see you in the next one. Welcome back. We're now ready to add the ability to schedule new launches through our NASA API. What was the endpoint to schedule a new launch? If we check our launches router, we remember that's the post to our launches collection, which calls HTTP add new launch in our controller. And if we scroll up, this function validates that we have the properties that we need, validates that we have a valid launch date, and then calls this add new launch function from our launches model.js, which we can find right here below save launch. This add new launch function works with our launches map So let's comment it out for now and replace it with a version of this function that works with our database. I'm going to call this new function schedule new launch, just to differentiate it from our save launch function that's right above. The save launch function will save a launch assuming that all of the properties on that launch are already set, particularly the launch flight number. On the other hand, our schedule new launch function down here will handle the same logic that our add new launch function already had, which is incrementing the flight number by 1 and then assigning a few properties by default. Properties that we don't need to send through our API because they're not things that the front end is concerned with. We can calculate these values on the back end. The new launch success will always be true by default, and a new launch will always be upcoming. That will always be the case when we schedule something new through our API. All right, so that's what we're doing in our schedule new launch function. But we're using Mongo this time. So we'll start by taking in this launch data and assigning those properties that we just talked about to their default values. So we'll create a new constant, new launch, and that will be equal to the launch with some additional properties assigned, which we can use the object.assign function to do. Just like before, object.assign launch, and success will always be true. Upcoming will always be true. And our customers list will always be 0 to mastery in collaboration with NASA. So we'll copy that. And things are starting to take shape. Now, what about this last property, the flight number? To get that, we're going to call our function right here at the top of our file that we called getLatestFlightNumber. So we're going to find the launch with the highest flight number in our database and then increment that by 1 when we schedule our new mission. So let's call that getLatestFlightNumber function and assign it to, say, a const that we call new flight number. That's going to be the result of awaiting the getLatestFlightNumber from our database and increasing that by 1. Just like that. Now we can set the flight number on our new launch to that new flight number by adding it to our list of properties here. We'll say flight number is equal to new flight number. With our new launch object all populated, I'll add a semicolon here, and we can now save our launch just like we did before with that save launch function that requires our launch to have all of the properties already set. So down here in schedule new launch, we'll await the result of save launch, passing in new launch. Looking good. Now, because we're calling await in our function, we need to make sure to make that an async function. And now we can export schedule new launch from our module. We're going to replace the call to add a new launch in our controller with the new function. So we can go ahead and get rid of add new launch in our exports, as well as the comment that we have right here. With our model file cleaned up, in our controller, let's make sure to call schedule new launch and pass in the launch data that we get through our request body. we know that the mission, the rocket, the launch date, and the target are all set. And in the model, when we schedule a new launch, we also assign the success, the upcoming, and customers fields, as well as that flight number, which we've spent some time on. Which means our launches have all the data that we need. Now, before I forget, in our controller, we need to make sure to require our new function here. So up where we require our functions from the model, let's replace add new launch with schedule new launch, just like that. And now we're using this function, which is async. So we're going to await it and make our controller function async, just like we've been doing with all of the other controller functions. I think we're ready. Let's double check our model. Notice that we don't need to export, for example, the getLatestFlightNumber function, because it's not being used outside of this file. It's not necessary to add it to our module exports, because it's only used in our schedule new launch function. It's an implementation detail, but not part of the core functionality for our launches. The only thing left for us is to test our code. Let's make sure there are no errors. NodeMon seems happy. So let's go to Postman and try to schedule some new launches. First, let's get the list of current launches to see where we're at. All right, we've created that one sample launch with flight number 100. So let's create our second launch. We'll set our launch data in this body tab here. We're going to be sending the Starship to Kepler 62F. Let's go. Our request succeeded. We got a 201 created response, and our launch data is being set. Notice that the flight number was set to one higher than the previous one. There's also this mystery property here that we didn't set. $sign set on insert? What's up with that? We'll answer that in the next video. For now, we have reason to celebrate. Our launches are being scheduled. I'll see you in the next one. Welcome back. What is this $sign set on insert property that's being set on our launches objects? Why is it intruding on our launch data? We didn't set this object, so what's it doing in our API response? To get to the bottom of this mystery, we need to look into our launches controller, so launches controller.js, where we schedule that new launch. Notice that when we set the response to our request here, we're setting it to the launch data that is coming in from the request body, which doesn't include our flight number or success properties or that mysterious $sign set on insert. So it must be that this schedule new launch function is mutating our launch object. It's changing the properties on it and adding the data that Mongoose gets back from our database onto the very same object that we pass in. Let's make sure that we're not crazy. We can console.log the launch that comes back after we've scheduled a new launch. Now, if we make a new post request in Postman, this time maybe our mission is up and away. Let's see what gets logged. Back in our terminal, we can see that set on insert is being set on our launch object when we schedule a new launch, which goes into our launches model, sets the properties to fill up our launch object, and then calls the save launch function, which over here calls update1 in our Mongoose model. Mongoose includes a feature where when you pass it a document that you want to update, like when we pass in the launch into the update1 operation, Mongoose not only saves the updates in MongoDB, but it also updates that launch object in memory. So that explains why we're seeing, for example, these flight number and success properties that we pass into our save launch function, and which we also see in our API response. But what about set on insert? We can find set on insert in the MongoDB documentation. And if we read into it, set on insert is used by Mongo to set the properties of our object when we do an upsert operation. It's this internal detail of how Mongo works that we're not directly using when we use Mongoose. Set on insert is being set by Mongo when we call our update1 function, the one that we see right up here. Because this launch object is being passed all the way from the controller when it comes in as the body of our request, and then back up when we send the response, we end up seeing this set on insert in our API response. That's crazy, right? In general, we want to avoid exposing this kind of unnecessary detail about how things are implemented in our API. In the response to our requests, we want to pass the client only the minimal set of data to fulfill that request, to minimize the amount of data that we send over the network, but also so we don't leak any data that a potential hacker might use to attack our database. We don't want hackers knowing that we're using Mongo and Mongoose, or how we're setting our response object, which we give away by returning this setOnInsert property. If there were a new security issue that was found in Mongo, this property might give the hacker enough information to start thinking about how to attack our website. In this case, less information is better. What we can do in our save launch function in the model, we can replace update1 with a similar operation, find one and update. This is very, very similar to update1. It still takes the filter as the first argument, the new object to update as the second, and it still accepts this upsert option. However, find one and update will only return the properties that we set in our update, the ones in this launch object. Let's try scheduling one more launch. We'll go up from our Postman response and make a new request. We'll call this one up NOA. And let's see what happens. Our response now only includes the properties that we expect. With our API working as we expect, we can now use our NASA launch system to schedule a new mission. This time it'll be to boldly go, which uses our ZTM, Starship, and off we go. All of our missions should be visible in our list of upcoming launches. We'll look at how to abort a mission in the next video. I'll see you then. Welcome back. We're at the final piece of functionality that we want to move into our Mongo database. How will we abort launches with Mongo as our database? This is going to be good practice to review how comfortable we are with Mongoose, with our models, and controllers. Let's start from the top. To abort a launch, we make a request using the HTTP delete method on our launches collection. This calls our HTTP abort launch controller function that first checks if a launch is able to be found in our database, and then proceeds to abort the launch with that ID, where the ID corresponds to a flight number. This exists launch with ID function is going to need to be updated inside of our model. It lives somewhere right near the top. Let's see. Right there. And it's one of the last remaining pieces that still uses our launches map. At the end of this video, we're going to completely remove our map from our project. So let's go ahead and commit to removing that. Now, how will we do our exists launch check in Mongoose? We want to find the corresponding launch with this ID in our launches collection. So what we'll do is we'll await our call to the launches database. That's our Mongoose model. And we're going to call not this has function, but a find operation to look inside our Mongo collection. We only care whether at least one document exists with that ID, so we'll use the find one operation and not the find by ID operation, because the ID in find by ID is the object ID, which we discussed earlier, that built-in Mongo identifier. But we're using our own identifier, this flight number, which we'll search for by passing in a filter into our find one call, which looks for a document matching the flight number, which is equal to that ID. So in Postman, what this would look like is the ID that we pass to identify which launch we're deleting or aborting will correspond to a flight number. All right, so back in our code, that means flight number must be equal to launch ID. And that's it. If our find one operation returns an object that's not null, a launch with that ID exists. All that remains is for us to make our function async, and we're good to go. Going back into our controller, we can now perform this validation. So now we need to make this abort launch function work with our Mongo collection. Actually, before we do that, let's make our function here async and call our exists launch with ID function properly. So I'll clean this up a little bit and move this check out of our if condition, and I'll say const exists launch will be the result of awaiting our exists launch function. And now in our if condition, we can check if not exists launch 404 launch not found. All right, what about that abort launch function? We can find it in our model underneath our schedule new launch right near the bottom. We already know, just like before, we're going to be calling operations on Mongoose. So it's going to be, that's right, an async function. And let's just comment this old functionality out. So let's see. When we abort a launch, we find that launch in our list of launches and update the upcoming and success flags, setting them to false. What's the Mongo equivalent of that? Well, we can use the update1 function, the same one we used earlier. Let's call await launches database dot update1, and we're going to be updating the document that matches this filter. Just like in our exists check, the launch ID here corresponds to a flight number. So flight number must be matching the launch ID. Now, the second argument to our update function is the list of properties that we're updating. What did we want to set? We wanted to set upcoming to false and success to false as well. Now, here's the difference. This time, we're not passing in the upsert parameter as the third argument here because we don't want to insert a document into our launches collection if one doesn't exist. In fact, we already know, because of that check, that one of these documents does exist, as long as nothing's changed in the database since we made that initial check. And even if something has changed in the few milliseconds between these two operations, well, our abort function here won't be inserting any documents because it's not an upsert. All right, so now in our controller, we can await the result of our newly async function here. And we need to do something in the result here. What we were doing before was setting the response code to 200 and returning the JSON object, which was aborted. This time, we're going to switch things up and be a little more clever. So we know in our model, we're going to want to return some value from Mongoose. So we'll return the result of our update1 function. And that's return, not return. With this change, how will our API respond to an abort launch request? Let's try making a new launch that we'll schedule. And let's keep it short. Let's say it's up and away. That will create a new launch with flight number 105. So we can now pass 105 as the ID in our delete request to trigger that launch being aborted. I'll send that request, and we got a 200 OK. Things seem to be working. But our response is this object with a bunch of metadata about our update operation. We have the amount of documents that were returned and the number of documents that were modified by our update operation, as well as things like how long the operation took and this OK parameter. So we could use all of this information to check that our response succeeded. We could check, for example, that OK is set to 1 and that the amount of documents that were modified to be marked as aborted is just 1. No more, no less. That's what this metadata here is for. It tells us about our update operation. Let's take advantage and do exactly that. Rather than returning the result of our update directly, we'll set that to a constant, aborted, and we'll return that aborted.ok is equal to 1, and that aborted.nModified, so the amount of documents that were updated, is exactly 1. That is to say that one document was successfully aborted. We can get rid of this old code now. It's served its purpose. And we'll have to do something in our controller with this result. Let's see. A big part of being a RESTful API, which uses JSON to transfer data in and out of that API, is to be consistent in returning JSON in all of the responses to all of your endpoints. What we can now do is check this aborted value that comes back from our model function and see if that's true or false. So if aborted is false, if not aborted, we'll return from our controller function, sending back a status code of 400 bad request. Something unexpected happened, and we either didn't update any documents, or somehow we updated more than one. So we'll return a JSON response, which passes back, just like above, an error that says, this time, launch not aborted. That's general, but specific enough for now. What about the success case? Well, if aborted is true, we'll return 200 and a JSON response that just says, everything is okay. So okay is true. Let's check to make sure everything works in Postman, making one more launch, this time with flight number 106, and we can give that a go with our delete operation. Everything is okay. What about from our mission control front end? Let's make up and away, going to Kepler 62F, we'll launch our mission and see if we can abort it. We have launch 107, and if we click this X, it's disappeared from our list of upcoming launches and should show up in the list of historical launches. Very nice. We've moved all of our core functionality to our Mongo database. I'll see you in the next video. Welcome back. You may have tried to run our tests from earlier in the course with the npm test command. And if you ran this, you might have noticed that our tests no longer work. What's going on? Why are the tests that succeeded earlier failing now? How do we get our tests to work when using an external database? To get to the bottom of this, let's dig into what's being logged. If we scroll through our errors, it seems like there's a few different things going on. Near the top of our test run, we're getting a warning from Mongoose telling us that it looks like we're running our tests in the wrong environment. We can click on this link here to find out more. We're taken to the Mongoose documentation on testing Mongoose with Jest. Remember, we're using the Jest framework for our tests. And this page starts off by telling us that it's a bad idea to use Jest for testing any Node apps, unless you are an expert developer with an intimate knowledge of Jest. Whoa, whoa, whoa. That's a pretty serious warning. But if I'm honest, this warning is a little bit overblown. As we're about to see, it's really not that difficult to use Jest with Node and with Mongoose. And many professional Node applications use Jest as the testing framework. In fact, Jest is the most widely used framework as of the recording of this video. The important part that we can learn from is this section down here, which tells us to use the recommended test environment rather than using Jest's default environment, which is designed to be used in browsers. We want to set our test environment to Node. And one way of doing this is by creating this jest.config.js file, but I'll show you an even easier way. If we go back to our Visual Studio Code, I'll close this terminal for now, and we can go to our package.json, not this one for the root of our project, but the one in our server folder here. So this package.json with our NASA Mission Control API, and we can add a Jest property here and set it to an object with some configuration options for the Jest framework. Jest knows to look inside our package.json for a configuration with some options if it exists. And in our case, it's going to be very simple. We'll set test environment using our double quotes, setting that to Node. Now that Jest knows we're not running any browser, let's try running our tests again, and I'll clear the console here, and we should no longer see that warning from Mongoose. Let's just wait for the tests to fail with a different error message. All right, there we go. We're still getting errors, but they're different than the ones we got before. So let's scroll up, and we can see that all of our tests are failing, and we're getting some messages about Jest not exiting, and below that we have this unhandled Mongoose error that's telling us that this launches.find one operation timed out after 10 seconds. So why are our database operations timing out when we run our tests? The answer is fairly simple. If we look at our tests file, remember that we're using supertest to start up our server by passing in this app object from the app.js file. And we use supertest to make requests directly against the Express server that's defined in this app.js file. The challenge here is that it's in our server.js that we actually connect to Mongo with our start server function that calls mongo.connect. So we're not actually connecting to MongoDB before we run our tests. And our tests are waiting around until they time out. How do we solve this? Well, the simplest way would be to copy over our connect call and run that before we do any of our tests. But we want to follow the dry principle. That's don't repeat yourself. If we're already connecting in our server.js file, we should be able to move this code into a common file that can be used both in our tests and in our server.js. Plus, our server code here is a little bit messy right now. We have this Mongoose code next to all of our server code. I have an idea. Let's move our connect function and our Mongoose event listeners to a file in our server folder under source. So I'll create a new folder, and there's a few different conventions that you might see for this kind of shared code that doesn't fall under the category of being a model or a route. You might see some people calling it a utility folder or utils for short. However, I like making it explicit that what's going to be in this folder, rather than just being general utility functions, are going to be services that are going to be available throughout the lifecycle of our server. So I'll call this services folder, and we're going to have one module inside of this folder for MongoDB. So I'll call it mongo.js. And what this file will have is all of the code where we use Mongoose. So I'll define Mongoose and require that. How do we use Mongoose in our server.js? Well, we have these two event listeners that listen to events on this global mongoose.connection object. So we can copy those over. I'll remove them from the server and paste them into mongo.js. And of course, we need to include the Mongo URL. So I'll move that right here at the top of our file. And we need this URL because we're going to be connecting from this file. So I'll copy over this mongoose.connect function and replace it with a call to some function in mongo.js that we're going to create. Let's define that function. In mongo.js, below our event listeners, I'll define an async function calling it Mongo Connect. And the body of this function will be that mongoose.connect call, which we're going to await the result of. Now we can export this function. So module.exports equals an object containing the Mongo Connect function, which we can now use in our server.js. And I can remove Mongoose because we're now using Mongoose purely through our mongo.js file. So right here below app, I'll require our new function. Using the destructuring syntax, we're going to be using the Mongo Connect function from the result of our require call in /services/Mongo. There we go. We can bring all of our imports together and call our Mongo Connect function in start server. Await Mongo Connect. Look at that. Our server.js file is already looking much cleaner and more organized. Trying to get our tests to work has given us a chance to improve the quality of our code. One of the extra benefits of writing testable code is that testable code is also just better all around for maintainability. What we can do now in launches.test.js, we want to require our Mongo service and call that connect function. So const, and we'll destructure, just like before, Mongo Connect from, this time, we need to make sure to go into that services folder. So we go up one level into routes, up out of routes, and then into services/mongo.js. All right, but where do we call Mongo Connect? We're going to use a feature of Jest, which allows us to set up an environment for our tests inside of a describe block, setting up whatever is required for the tests included in that block. We're going to want our Mongo connection to stay alive for both our get tests for the launches collection as well as our post tests. So we can do something a little bit clever and wrap both of these describe blocks in another describe block. So I'm going to create describe and say that what we're doing in this file is we're testing the launches API, and the way we're testing our launches API, described in this callback here, is going to be described in these two blocks. So I'll copy all of our tests and paste them into this new describe block. Now we have this nested structure where we have the launches API tests grouped by the HTTP method, and each HTTP method has some tests that need to succeed. With this change, we can now add a setup step to our launches API tests, which we can do with this before all statement, which takes a callback that needs to run before all the tests in this block are run. Whatever is in this callback will run once to set up all the tests that come after. What we want to set up is our Mongo connection by calling Mongo Connect, which is an async function. So we're going to await the result and make our callback async. Looks good. Let's see if that fixed our tests. Let's clear the console here and run npm test. All right, waiting around. And we have more tests that are passing, but there's still some errors. The good news is that we've already improved our code and we're making progress. Let's figure out the rest of the errors in the next video. I'll see you soon. Welcome back. Let's keep fixing our tests and get to the bottom of this last failure. 3 of our tests are passing while 1 is still failing. And our test logs are still giving us some helpful warnings. Jest is still not exiting 1 second after the test run has completed, and this usually means that there are asynchronous operations that weren't stopped in your tests. One thing that we can try doing here is explicitly disconnecting from our Mongo database when our tests complete so that the connection doesn't stick around forever. That means we need to export a disconnect function from our Mongo service. All right, let's see. We're going to make a function to disconnect from Mongo. So Mongo disconnect. And guess what? Just like we connected, we can disconnect by awaiting the result of mongoose.disconnect. Mongoose already knows which database we're connected to, and it'll disconnect all the connections to the currently open database. Let's do our bookkeeping and make our function async. and export it from our file. Looks good. Let's see if this fixes our problem. Now in our tests, we'll import that Mongo disconnect function. So let me move this over to its own line and add Mongo disconnect. Now to run Mongo disconnect when all of our tests have completed running, we're going to use the teardown equivalent of our setup function here. So the opposite of before all is after all, which is going to do something very similar to our setup. We'll have an async callback here where we await Mongo disconnect this time. Will our tests run now? Only one way to find out. Let's run npm test. All right, it looks like my suspicion wasn't correct. Jest is still not exiting once the test run has completed, even after we've disconnected from Mongo. Maybe it's a good idea to follow Jest's advice after all. If you are paying attention, you notice that it's telling us to consider running Jest with -- detect open handles. We can use this parameter, this flag, by adding it inside of our server's package.json when we run npm test. It's a parameter that we can add to our jest command. So now we'll run jest -- detect open handles, and let's see what happens. We can see our parameter was set at the top of our logs here. Jest -- detect open handles. With this change, are our tests succeeding now? Let's see. Scrolling to the bottom, we can see our tests are hanging. And if we scroll up slightly, we still have this one open handle and one test failing. Let's see why. No matching planet was found when we post to the /launch collection and we expect the 201 created response. Let's see what might be happening. In our launches test, we'll find the corresponding error. This is the one. It should respond with 201 created. And when we pass in this complete launch data, we're not getting a 201, but instead, let's see, we're getting this error that's being thrown saying that no matching planet was found. That's right, we added an additional check in our API to make sure that the planet that we're targeting in our launch is one of the planets that we've marked as habitable in our planets collection. Let's see what we're actually passing in our test. We have complete launch data up here at the top, where our USS Enterprise mission is targeting Kepler-186f. This is not one of our potentially habitable destination exoplanets. Notice it's not in the list. So let's replace it with one of the planets that is in this list. Everywhere we have Kepler-186f, let's replace it with Kepler-62f, both in our complete launch data as well as our 2 error cases. Now our launch target will always be a valid planet that's stored in our database. I think we've done it. Are you with me? Let's see. I'll clear our console here and run npm test one final time. it looks like our test passed, but right now we can't see the results because of this watch screen here. So I'll quit watch mode with Q, and instead I'll change directory into the server and run npm test from there. This watch mode here is coming from the tests in our front-end client. Because when we run npm test from the root of our project, we run both the server tests and then the client tests immediately after. So back in our terminal, let's run just the server tests. Check it out. 4 passed out of 4 total. Very nice. Before we go, it's worth noting that what we're doing here is writing tests that actually talk to our real-life database to create launches. Every time we run our tests, a new launch will be created in our front end. We can see this if we go into Postman and make a GET request to our launches collection. Let's see what's coming back in our launches. Notice at the bottom of our list, we have this USS Enterprise mission that's targeting Kepler 62F. That's the launch that we created when we ran our tests. So we might want to be careful with the conditions under which we run our tests, because they can change the data in whatever database we're connected to. The tests that we're running could almost be called integration tests or end-to-end tests, because they test the real-life connection all the way down into our real-life database. If we were running these tests very often, we would want to create a specific test database for our test data and separate out a production database that we use for our real-life launches. That way, if we make a mistake in our tests and accidentally remove all the data, well, our production data won't be affected. Just something to consider. But we should be proud of what we've accomplished. We've written our tests in a way that includes our database as well as the API when we run it. And we've used this opportunity to clean up our code and create our Mongo service, which handles our Mongoose connection. All very good stuff. And with that, I'll see you in the next video.